Hi, one more video tonight, and then I think it's time to take my dog for a walk. Um, in 4.1, we talked about random variables, and there are going to be two really distinct types of random variables. One of the two that we're introducing in chapter or section 4.3 is discrete random variables. And then when we get to chapter, I want to say 6, we introduce continuous. But the type of random variable really depends on the support values. So the values that the random variable can take on. Um, the values a random variable could take on could be finite. For example, the number of heads when you flip a coin twice can only be 0, 1, or 2. Um, I could also, this is another discrete random variable, the support values could be infinite, but I can line them up naturally, for example, with the natural numbers and count what they would be. So it might be infinite, but it's what we say is countable. You could actually, in reality, we can't list them all, but we can see exactly the nice pattern 1, 2, 3, 4, 5, and match them up one to one with natural numbers. So these are going to be discrete. So if you have either finite support or infinite support, but you could practically count out all the values, we're going to say you have a discrete random variable. If the support is uncountable, then this is going to be a continuous random variable. And uncountable is something, again, there's an interval or there's a range of values. You can't put your finger exactly on one value. It could be anywhere in a range. You're never exactly right on one value. It's not countable. So maybe examples would help best. Here's some that we looked at in class. So back to milk duds again. I'm still stuck on those. Number of milk duds in a snack size box. There's only going to be a finite number, and so your support would only have in maybe 0, 1, 2, 3, 4, 5. Number of frogs with an additional set of chromosomes. Again, finite. There's only so many of these frogs, and only so many of them would have this extra chromosomes. Number of libertarian voters in Terre Haute in November. Maybe 0, 1, 2, 3. But, I mean, it's going to end somewhere, right? There's a nice finite number. Back to the golfer swinging. Could swing infinitely many times before hitting the ball, but I can line it up nicely. I could say the number of times could be 1. It could be 2 swings. It could be 3 swings. And, I do agree. It could go on forever. I can't make dots here, but the point is, I can count out. I could really essentially say it's 1, 2, 3, 4, 5, 6. Let's give you the opposite. Let's give you an uncountable. The height of your grandmother. It's anywhere in a range, right? An interval, somewhere in an interval. The amount of time you're going to spend on test number 1. I mean, again, I agree. It's probably in a finite range, but it's anywhere in that interval. It's any real number in an interval between let's say 0 and 60 minutes. So the type of support is going to influence the way you model the mass function or density function of your random variables. So down here I just gave a couple examples that we talked about in class. And when you do define this nice function, I told you in the other chapter we call it P of x. I mean, f of x, P of x, they're all functions. A couple properties of this function. P of x is 0 for anybody not in the support. So if I don't list the support value, I'm assuming that its probability is 0. The probability x takes on the value xi is just written P of xi, and all these better be positive. And the sum of all the probabilities at these support values better sum up to 1. So I have this nice function P, and it just defines the probability of values in my support. And a couple nice properties. So again, it adds to 1. They're all positive. Here's an example we used in class. I gave, here's 3 possible different functions for P, and notice that there's only one of them that's legal. I mean, I know this is illegal function, a mass function, because you can't have a negative, and P of 2 is illegal because it sums up, if you add these, 0.7, 0.9, it adds up to more than 1. So, and then the rest of this chapter is really just building functions for these random variables, like mass functions, the probability x is equal to 2, 3, 4, 5. And I mean, this one actually, the outcome of this looks easy, but if you were in class, which like the other class, we actually spent a little time building this function. This wasn't something that I just sat down and said, oh, it's x, x minus 1, choose 1, and I knew right away. We built this we built it first for the value x equals 2. I mean, what's the probability that he's done with this drill in 2 shots? That means he made both shots, which is 0.77 times 0.77. And then what's the probability he does it in 3 shots? That means he made 1 out of the first 2, but he missed. But he made 1 out of the first 2, and then he had to make the last one. So he made 1, he missed 1, and how many ways can you make 1 shot out of 2? So that's where we got the probability x is 3. So, I mean, we built this from scratch. We found a nice probability density function for it and then wrote it out. So it wasn't like it just came to us. It took a little bit of work. Same way with this one. We built it from scratch. This, you might notice if you took statistics, it's a very nice binomial distribution. And then, again, you can write it more succinctly this way. But, it took us a while. I mean, what's the probability that you get no red lights, and what's the probability you get all red lights? These are easy cases, and then in between, just figuring out all the other cases. But the mass function is really just finding what's the probability at each of your support values for this random variable. And then the graph is very nice. You're just plotting the amount of probability at a discrete point. And so we just did a bunch of examples. Minimum of 2 numbers when you roll a die. We switched from a mass function, and then you'll see down here we switch from a mass function to a cumulative density function or distribution function, just to show you how to go back and forth. I guess we started with capital F and went down to little p, which makes sense. You can see I pick up probability at 2, I pick up probability at 4, and I pick up probability at 5, and that's where these values are coming from. And then I did a little video clip. This is really kind of funny, I think. She's one of my favorites. Molly Shannon, I think she's really funny. But here again, this didn't just come out. This is kind of like the Keno game, trying to pick, with lottery or something, numbers successful picks and unsuccessful picks. But I mean, we wrote out the first couple cases first, and then saw there was a nice general formula for it. So with all these, we had to use techniques that we did, back in chapter 2, using counting or thinking about how to make probabilities. So it wasn't, the random variable idea is nice, but the hard part again is finding the function that fits it. And in chapter 5, actually, we'll start looking at classes of these random variables. So it does, when we get to 5, it'll get a little bit nicer, I should say, for a while. Not easy, but nicer. At least they'll have a pattern. And right now, you're just trying to pick out density functions that go with any situation. So I think that's it for my videos tonight. And so let me know if you have any questions.